Okay, I want to look at static RC circuits. So I'm not looking at charging the capacitor. I'm not looking at discharging the capacitor. The circuits have been hooked up for a long time, and typically that's literally the word they'll use. They'll say the words they'll use. They'll say, you know, this has been in a steady state, or this has been a long time, and it's long enough that everything is charged. So if you look at these scenarios here, this is a certain voltage, and while this thing was charging, of course, there was a current, but eventually the capacitor is going to get charged. It's going to get to a charge equal to CV, but eventually this gets a total charge accumulated on it that's only that is limited by the battery you put in and the capacitance of the capacitor, but eventually this current is zero. So after a long time there is no more flow of current, because the capacitor is fully charged. It's fully charged when it gets to the exact voltage of the battery, right? Battery gain, battery loss, no voltage over here, no current over here. So in this situation, after a long time, there'd be no current flowing anywhere in the circuit. Here, this thing's going to charge, but eventually it gets charged and it gets to be the voltage of the battery. It stores a certain charge based on its capacitance and based on the battery. But this thing is free to flow the whole time, and it just continues to flow. Okay, and it also just has the voltage of the battery. And so if you wanted to find the current in that guy, you can just do V equals IR. It's as if the capacitor isn't even there. Again, this parallel thing doesn't affect the flow of charge here. Now again, at the beginning when you're charging this, things kind of get a little funky. You're just going to draw more current out of the battery, but this still always gets the same current because it gets the same voltage and it's got a constant resistance. But as far as the total current flowing from the battery while this is charging, it's different. But after a long time, this is fully charged. Obviously no current flows here, and all we have is this just going around and around and around. And how much? Well, you tell me the voltage of the battery and the resistance of the resistor, and I'll tell you the current. Okay, over here, eventually, here's our battery, and we got, let's say, R1 and R2, and we have this. Well, what voltage does this get? Does it get the voltage of the battery? Eventually, again, it gets charged, and after a long time, it's fully charged. And what happens? Well, eventually, this is fully charged, and so no more current flows through R1, so eventually, I1 equals 0, and what does I2 equal? Well, this doesn't prevent this from flowing at all this way. And so eventually the flow of charge just happens to here, and you could do it your own. V equals I2 R2. The voltage over this guy is the same as the battery because this is in parallel with the battery. So you can just use the battery and the resistors to resistance and figure out the current through 2. And the current through 2 is just going to be based on that. The voltage over the capacitor, again, is the same as the voltage over this, which is the voltage of the battery. Okay? All right, how about this guy? There's our battery, there's our capacitor, here's R1, and here's R2. And what's happening here? Well, eventually this gets fully charged. And the question is, well, what voltage does it get? Well, when it's fully charged, it's kind of like it's not even in the system. Charge is going to flow like this. Charge up by the battery, down R1, down R2, and back. So what you can say is that V equals I R, where R is in fact R1 plus R2, right? They're in series with each other. So you can say that V over R1 plus R2 is then the current flowing, but the current flowing there is the current flowing here. Okay, so then what's V1? Right? V1 is its own I times its own R, but V1 is what? V1 is the current flowing here, but we already decided that that is the total current. V over R1 plus R2 times R1. Okay, and you can see then that V1, the voltage over R1, is equal to R1 all over R1 plus R2 times V, and so V is some fraction of the total voltage. Why is this important? Well, because V1 is the voltage over the resistor, which is indeed the voltage over the capacitor, and you need the voltage over the capacitor to see how much charge is stored on the capacitor. Again, in this case, eventually the voltage of the capacitor was the battery. The voltage was the battery because they're in parallel. Here, the voltage was the same as this guy, but this guy was in parallel with the battery, so that voltage is the battery, but not in this case. The voltage over this is the same as the voltage over 1. The voltage over 1 is not the full battery. V1 plus V2 equal the battery. So the voltage over R1, which is equal to the voltage over the capacitor, was some fraction. Okay, something similar here where you get a little weirder, where you have like R1 and R2, and it's basically this same thing. The point of this whole thing is that there will be current flowing. It'll go like this, and it'll go down this branch, and then it'll go down that branch. Again, the resistor could be here and here. It doesn't matter. There is a path through this circuit, through the resistor, down this way, that it will continue to flow even after a long time. Now, these capacitors will get charged. They'll accumulate a certain charge. And how much charge will they get? Well, that will depend on their voltages, right? And their capacitance. So they each have their own C and their own V. And what's this voltage? Well, this voltage is the same as this. Whatever V1 is, that's what goes there because those two things are in parallel. And whatever this voltage drop is, that's what's going to go there. You find those voltage drop the same way we did over here. The total voltage equals the total current. The total current does flow through here. The total current is R1 plus R2, so it ends up being a very similar calculation. Again, you have to be able to look at RC circuits in a static situation, meaning they've been charged for a long time. And again, just think about what's getting current. Can current still flow through? Like in this case, current can't flow anymore. In this case, current can continue to flow. Current has a path not down this branch, but it has a path down this branch. These two then have to have the same voltage. These have the same voltage, so current can flow here. Find the total current. Once you know the current in R1, which means you know the voltage of R1, which means you know the voltage of the capacitor. And this is a very similar story. Again, lots of the AP questions and situations won't have you be charging or discharging the RC circuit, so they'll just give you some static situation and say, hey, this is, it's been hooked up for like 2 minutes. What's all going on here? And you have to be able to think about where is current flowing, where is the current equal to 0, how big is the charge, because how big is the voltage, and a lot of it is just understanding that things in parallel have the same voltage. Okay, hopefully this is helpful in looking at RC circuits.